Emma is a native of Maryland and now residing in Washington, D.C., who as a loyal Marylander decided to circle through a large state like Pennsylvania and find this great Department of Environmental Science and Technology here at UMD in the friendly state of Maryland. Several of us, including Dr. Nigahban Azar, Paul Liesnam, Hubert Montas from BioE, Puneet Srivastava, Amanda Rockler, and myself, and Dr. Nigahban Azar being the PI, we received the USDA NIFA funding in 2022 for about $750,000. So with that funding, we had some graduate students, and Dr. Marty Ravenhurst is very well aware of that, so he moves the graduate applicants to our side. So we located actually 2 students from environmental science program, Jen Steeple and also Emma Gray, and we thought that their background fits to our project, and Jen Steeple graduated last year, and Emma has been working since September of 2023 with us. Her degree is in environmental sciences from University of Pittsburgh, a BS degree in other words. She graduated with a GPA of 3.65, magna cum laude in April 2023, was on the departmental honors in 2023, and Dean's List from 21 to 23. So, and received the sustainability distinction in 2022. She had applied to our graduate program, as I mentioned, and we had an interview via Zoom, so we definitely realized a good fit. And she came to us with huge accomplishments and experiences, including 2 technical presentations, one on resurrecting a half-century coal supply chain records. And you know that coal mining and all that has been a little bit controversial in our country here. And work was done by her as a Mickey Leland Energy Fellow at the National Energy Technology Lab in Albany, Oregon, for that work in summer of 23, right before actually she joins us. She also had experience as the undergraduate research assistant at the Pittsburgh University, both with the atmospheric chemistry group as well as with the remote sensing group. So you can imagine the background that she had. And academically, she also had a semester of study abroad in Edinburgh University in UK. She has some awards and honors to her credit, including 2023 ENERGIS Scholar, which is awarded to 1 student annually for outstanding geospatial scholarship in Appalachian region. And also she has the UMD Dean's Merit-Based Scholarship, which she received in August of 2023 here. And teaching, she actually was involved in educating K-12 kids in Pittsburgh Parks Conservancy while she was doing her BS degree there. And she was GA for ENST 233 with Dr. Yonkos. I don't know if he's in the audience, but maybe listening to us via Zoom. And extracurricular activities, she has been president of GATES, Graduate Association for Technology and Environmental Sciences, and also she contributed as volunteer for an Anacostia watershed cleanup efforts. Yeah, Dr. Yonkos is right there sitting. All right, well, so she, he's going to tell how, another half an hour he'll take how good you did. Her presentations in Maryland so far has been really ASAB 2024 Annual International Meeting in Anaheim, California. ASAB is American Society of Agricultural and Biological Engineers. And her AGNR Cornerstone presentation last fall. And MAS's Climate Actually Symposium workshop that was held last Thursday in the Student Union. And she also has a paper with our postdoc, Mohammad Reza Yazdi Samedi, for ASAB's upcoming annual international meeting in Toronto. So she's working the final chapter of her thesis. She's planning on defending her thesis this semester. She may not meet the graduate school deadline to submit, but she may become graduate of the summer session. It is not any fault of hers, to be honest with you. There was a lot of work, so maybe if anybody blame on me, and maybe Masood. So some, on Dr. Liesnam there. Okay, her hobbies, she likes drawings, and she made some of those drawings in her presentation. Okay, I'm just warning, if you find it, you can locate it, and maybe she'll give a, give
I'll shout it out.
Okay. Also likes biking and cycling. It has been really a joy to work with Emma. She's really hard worker, and you can see all around great graduate student, and I'm proud of you, Emma. I think the floor is over.
Okay, well, without further ado, my current research is titled Assessing the Socio-Economic Feasibility of Reclaimed Water for Irrigation with Agent-Based Modeling. And so I'll go through just some backgrounds, introductions, and motivations for the work, as well as some overarching research goals and questions I had, the methods I used, the study area we looked at, and then some results, takeaways from those, and some concluding thoughts and areas to continue with. So to start, agriculture makes up around 34% of total US withdrawals of water. And of this 34%, around 48% is groundwater, which is around 57 billion gallons per day, just to put it in perspective. The surface water you see here is primarily in the southwestern region, while the groundwater is primarily in the central and eastern region. And we also know that irrigation is increasing heavily, especially in our area, due to reduced precipitation. You can see on the graph on the left, precipitation has decreased drastically since 1900, and that's for the growing season, June through August in Maryland. And we also see that irrigation has steadily increased despite farm acreage decreasing over the last almost 30 years now. And irrigation is really helpful in boosting crop yields. It can improve water use efficiency, but it also draws down a lot of groundwater. And so in the Aquia Aquifer, which is one of our main aquifers here in Maryland, we find correlations of around 79% of our drawdowns in our groundwater is correlated to agricultural use. And we also see this in Calvert County. We see groundwater declines upwards of 100 feet. And so when we decline groundwater significantly, we can permanently reduce aquifer capacity, cause saltwater intrusion and land subsidence. And so this is really a resource we want to preserve for the future of Maryland. And one way to do that is by diversifying our water resources with alternative water. And so here comes in reclaimed water. Reclaimed water is treated wastewater. It's also known as recycled water, potable reuse, or water reuse. And there are two main pathways to use reclaimed water. The first being indirect potable reuse, or IPR, and the second being direct potable reuse, or DPR. And how IPR works is, so we treat our water at a treatment plant. This gets discharged into a lake or a large body of water, and it will buffer. And then this water is later drawn up back into a drinking water treatment facility, where it can be discharged, or it can be treated and then discharged to consumers to drink the water. However, with DPR, we can connect this cycle and use a more advanced treatment and discharge our water directly to a drinking water facility to be discharged to consumers. And this actually already happens in our region. For anybody drinking DC water, they use IPR. Our wastewater treated wastewater goes into the Potomac River, is drawn back up into the Washington Aqueduct, and DC water pools from the aqueduct to treat its water and distribute to consumers. Similarly, in Fairfax, UOSA or Occoquan uses direct potable reuse. Their wastewater treatment facility actually discharges directly to their drinking reservoir, which then draws up water to treat and discharge their customers. So these processes are already being used. How would that look for irrigation though? Now we draw on groundwater for irrigation, produce our food, humans consume that, produce waste, and our waste goes to a treatment plant. But we can't connect this cycle because of barriers such as regulations and social concerns and economic concerns. But when we employ more advanced treatment, we can actually reduce some of those barriers and connect this cycle called the circular economy. Some major benefits of using reclaimed water or treated wastewater for irrigation include, like I said, increasing our water supply, promoting that circular economy. This can also promote social awareness in farmers and support sustainable agricultural development. It has benefits with soil fertility, and it can also help address climate change directly. However, like I mentioned, there are several barriers that prevent the widespread acceptance of reclaimed water. These are global barriers. One includes lack of infrastructure. Most treatment plants can't or don't currently have the infrastructure to treat their water to the advanced level required. Another would be social perceptions. There's like an associated yuck factor. Consumers think the water is inherently grosser, or that their crops will be dirtier. There's also regulatory burdens. Some states don't have regulations for reclaimed water, and so it can't be used for irrigation. Another would be cost of infrastructure. Some of the costs to construct the pipes or installation materials, things like that, are more expensive and can cause economic barriers. There's also a lack of available reclaimed water in some regions, so we're highly dependent on the volume of treated wastewater in that region to determine feasibility. And lastly, in some areas, there's also lack of communication and coordination, and this can cause stakeholder conflicts. However, in Maryland, Maryland Department of Environment regulations state that Class 4 reclaimed water, so our highest level of treated wastewater, can be used to irrigate commercially processed crops and non-food crops in Maryland. So that gets rid of that barrier. Another one, Maryland wastewater treatment plants already employ fairly advanced treatment because we discharge into the bay, and the Chesapeake Bay watershed has pretty advanced nutrient management plans, so we follow those. We also have two amazing agencies, Maryland Department of Environment and Agriculture, are already interested in promoting reclaimed water for resources and for agriculture, so we get rid of those. But that leaves social perceptions, cost of infrastructure, and lack of available reclaimed water as some unknowns in our region. And so I wanted to focus on those to ask the question, what are the biggest barriers to reclaimed water irrigation in Maryland, and how could we overcome them equitably, focusing on those three barriers I just mentioned. To do that, I focused on three main goals. One was understanding the economic costs and benefits associated with reclaimed water irrigation. The second being understanding perceived barriers of reclaimed water irrigation in Maryland. And the third would be combining those social and economic dynamics to simulate successes and challenges of reclaimed water irrigation in our area. To do that, here are my 4 methods and my doodles. The first, I wanted to look at the net benefit from irrigation, seeing if some of the benefits from irrigation could cover costs associated with reclaimed water irrigation. The second, we employed a stakeholder survey to get an idea of what farmers thought about reclaimed water irrigation. The third, we employed an agent-based model. And the fourth, we're looking into some scenarios that we can analyze with our model to potentially support policies and other programs that might increase the adoption of reclaimed water irrigation. And these methods were applied to 2 watersheds in our region, the Zakia watershed in Southern Maryland, or Charles County, and the Greensboro watershed in Eastern Maryland and Delaware, which is also Queen Anne's County. Zakia watershed is a lot less agriculturally intense. It's around 15% agriculture, and it's mostly forested with some residential areas, but it's also a lot more racially and economically diverse. To contrast that, we have Greensboro watershed, which is a lot more agriculturally intense. It's around 55% agriculture by land use, and but it's a lot less diverse. And so we wanted to compare these 2 watersheds to see how these differences might impact overall acceptance of reclaimed water. So getting into that first, net benefit from irrigation. Reclaimed water irrigation has a lot of costs that can introduce disparity among farms, especially when we have different financial capabilities within farms. So the net benefit approach looks at if economic benefits from irrigation can eliminate some of those cost barriers associated with reclaimed water. What do I mean by benefits? So for example, if we have a stalk of corn that's rain-fed, it might produce 1 ear of corn. But if we provide irrigation to this stalk of corn, it might produce 2 ears on a good year. And so that's a net benefit in irrigation yields of around 1 ear of corn. And so our previous postdoc, Asbina Rahman, calibrated a SWAT model, or a soil and water assessment tool, for our 2 watersheds to predict crop yield benefits and irrigation demand for 3 precipitation scenarios. One would be for a wet year, so this year in orange. The second would be for an average year in gray here, and then the last would be for a dry year, which is yellow. This is just precipitation over the growing season, so May through September. And for every single scenario that she tested, she found that yields increased for both corn and soybean fields. So regardless of if there was a wet year, there was still some increase in yield. And so we wanted to see if these yields could cover some of those costs. What do I mean by reclaimed water costs? For this preliminary analysis, we only consider conveyance cost and cost per volume. Conveyance cost is the cost to pump water across a gradient. So for this, it'd be pumping water from a treatment plant directly to a farm. And cost per volume, which is the money per cubic meter of water. This is typically paid directly to a treatment plant and can guarantee water quality and reliability. And for cost per volume, we consider 0 cents all the way through 30 cents per cubic meter, but nationally it can be 10 cents to 50 cents. And so these were the costs we considered. Additionally, we have reclaimed water capacity limitations in the regions. This is the Zakia watershed. We have 2 main treatment plants in this region, and they have a combined capacity of around 400 million gallons per year. But in a given average precipitation year, we had simulated a total water requirement for irrigation around 767 million gallons per year. So let's see, this was a deficit of around 360 million gallons. So we couldn't provide to every single farm if they all chose to irrigate with reclaimed water. Similarly, for the Greensboro watershed, there are 3 main treatment plants in the region, and these have a combined capacity of around 4,500 million gallons per year, but an average year would require around 5,300 million gallons for irrigation. So again, we have a deficit of around 800 million gallons per year. And so what we find with our preliminary results is that the Zakia could provide its entirety of reclaimed water capacity to farms, which would serve around 234 farms, or 1,200 acres, while Greensboro could provide some of its capacity, which would serve around 1,200 farms. And so while Zakia is limited by capacity, Greensboro watershed is limited more by costs. And this is demonstrated here in the figures on the right. These 2 on the left show when cost per volume is 10 cents per cubic meter, versus when it's increased to 20 cents, no farm in Greensboro can afford that cost. So the difference in unit cost definitely impacts whether that benefit is helping or not. And so some main takeaways from our preliminary analysis were that the benefits can cover some of the costs associated with reclaimed water, but major costs like distances and unit costs must be considered further. But this could significantly reduce groundwater consumption. Next, moving on to some of our stakeholder survey findings. So we employed a stakeholder survey, which was a paper survey with 24 multiple choice and write-in questions. And we distributed this at 6 meetings across Maryland. I wanted to point out that the survey was heavily inspired by a few studies before me, as well as some preliminary analyses or preliminary results acquired by some of Paul's team. And the survey had questions about their farm, like if they leased or owned it, their farm size, or how far they thought they were from a treatment plant, as well as the crops they grew, their water resources. It also asked questions about how they rated their own knowledge on certain factors like climate variability or water conservation. It also considered, it also asked questions about how they thought their neighboring farms might affect their own decisions, both in irrigation and reclaimed water adoption. And it asked things about farmers' own demographics like education, age, race, sex, and net income. And so to start, we collected 64 surveys, most being from Central Maryland and Eastern Maryland, mostly because that's where the agricultural meetings were that we went to. And so the demographics we found were that most survey respondents were 65 or older, had a high school or associate's degree, were male, were white, owned the farm they managed, had farms over 180 acres, had been farming for 30 to 59 years, and had net income of less than 40,000. When asked about following which factors were most important in farming decisions, with 10 being most important and 1 being least, farmers ranked economic benefit as the most important, so an average of 7.6 out of 10, the second being their own experiences and knowledge, and their third being water conservation. Asked about their knowledge, they ranked their own knowledge and climate variability a 5.4 out of 10, water conservation a 6.1 out of 10, irrigation systems a 5, and reclaimed water a 2.5. And of respondents, the majority had no experience with alternative water resources. However, 11% did, mostly from rainwater harvesting, but 2 respondents did have some experience with reclaimed water. And experience here could mean a facility tour, a friend of a friend using it, attending a workshop, anything along that would fall under experience. Getting into the meat, we asked if reclaimed water irrigation was fully feasible for their farm, what farmers would do about it. Around 48% said that they would partially or fully invest in reclaimed water irrigation. Another 20% said that that would make them want to research reclaimed water more, and the final 32% said they would do nothing about it. When asked about the biggest barriers that they perceived or their biggest concerns about reclaimed water irrigation, the first was cost infrastructure, the second was reclaimed water infrastructure, insufficient reclaimed water, and the third is lack of infrastructure. So these kind of line up with our three main uncertainties that we saw as well. I also ran a quick test to see which attributes were most significant in farmers' acceptance of reclaimed water, and I found 5 to be significant. Attitude toward cost share, so farmers that were more willing to accept a cost share program from the government were also more willing to accept reclaimed water. Farmers who had a higher perception of water quality or reclaimed water quality were also more likely to accept reclaimed water. Those who had more positive attitudes towards government regulations were more open to reclaimed water. Those who had larger farms were more open. And lastly, farmers who leased the land instead of owned were more open to reclaimed water. And then of near marginal significance, so almost, farmers who had some experience also tended to be slightly more open. And I do want to note that for social sciences, R-squareds tend to be a little lower, which is why you're seeing correlations that are a little lower. And so some final takeaways from our surveys. We found respondents to be disproportionately white males compared to the Maryland Ag Census. So this is something that we'll consider when we're inputting data into our agent-based model so that we get a more representative population. But overall, there are 6 driving factors of reclaimed water acceptance that we found to affect our survey respondents' openness of reclaimed water. And so these will feed into our social aspect of our agent-based model. And then lastly, I want to highlight that around half of our farmers surveyed expressed at least moderate interest in reclaimed water. So this is a really positive sign for reclaimed water acceptance. So getting into our modeling, I know you all are asking, what is agent-based modeling? Agent-based modeling is a bottom-up modeling approach, and it focuses on 3 main things: heterogeneity, spatial structure, and adaptation. And so agent-based models are based on agents. Agents are individuals within a system. For ours, they're farmers, but in the model on the board here, you can see that agents are wolves and sheep. And basically, agents are assigned attributes, and based on their attributes, they can have heterogeneous behavior and decision-making structures. And so we can see the emergence of patterns from those dynamics. So for the example on the board, this is the predation model. It's a really classic model, and it looks at how sheep and wolf dynamics are affected by resource availability. So wolves are in black, sheep are in white, and grass is in green. And when sheep eat the grass, they can reproduce. And when wolves can eat the sheep, they can reproduce. And so you can test the starting number of sheep, the regrowth rate of grass, and you can see how population dynamics might be impacted by these dynamics. Agent-based modeling have been used in a number of fields. I just wanted to point out that it's a really widespread practice. It's been used for disease spread in deer, diffusion of ideas through word of mouth, vaccine optimization, and social segregation in neighborhoods. But for our model, our agents, like I said, are farmers, and they have 2 decisions. One is if they want to irrigate their farm, and the second is if they want to use reclaimed water or groundwater if they decide to irrigate. So our agents are first assigned attributes. These are like what we discussed earlier. They're socioeconomic demographics, their farm attributes like farm size, what kind of crops they grow, as well as their knowledge, beliefs, and attitudes. So are they more open to reclaimed water? Do they have experience? Things like that, as well as a social network or social influence. And I'll discuss what that means in a tiny bit. But farmers are sent through this framework, and for each decision, they have to flow through this chart. So it'll check for profit. Is the decision profitable? If they have enough money, they'll say yes and move on. And then we can check for water availability. In our case, it would be, is there sufficient reclaimed water in the area? If there is, they'll move down further and check and see if they are socially suitable for reclaimed water. do all of their social factors align with reclaimed water acceptance? Like, are they open to cost share? Are they open to regulations? Do their neighbors, are they open to it as well? And if all of these say yes, they will completely adopt reclaimed water. However, if they only partially accept reclaimed water, they're still a little skeptical. They might have a mixed use of reclaimed water and groundwater. And if they're completely hesitant or they want to reject reclaimed water socially, they can default back to groundwater. The same would happen if they have the money to afford reclaimed water, but there's no water available in the treatment plants, they would default back to groundwater as well. And so when I define financial profit, here we consider all the market costs associated with reclaimed water. These would include irrigation infrastructure if they don't already irrigate, well installation infrastructure if they don't already have a groundwater well, if they choose to use groundwater, and then reclaimed water infrastructure such as piping, storage tanks, as well as that unit cost and conveyance cost that we talked about earlier. And then lastly, cost of production for their farm. And then the benefits considered here would just be crop sales for that year, that season. And when we talk about infrastructure, I wanted to point out that the distribution systems for our AVMs are a little more optimized. Like in the preliminary analysis, we talked about how we wanted to optimize distances. And so we established this backbone irrigation system, which allows for pipes to follow major highways. And then from that purple pipe system, we can create smaller pipelines to farms. And this can limit some of the costs associated with building those pipelines and installing them. And so when we discuss social feasibility, we're talking about those 6 drivers of reclaimed water again, as well as farmers are placed in a social network of farmers. And so for our model, we use a scale-free network. And what this means is that for any given node in a neighborhood, let's say, a farmer is somehow connected either by a friend of a friend of a friend or 8 friends later. At some point or another, that idea will spread to that farmer. And this can be used to model the diffusion of ideas across a big area. And so some preliminary economic results. Our models are currently separated into 2. We have an economic portion and a social portion, and these will be linked. But right now, the economic model states that when there's no limitations on water capacity in the area, 80% of farmers could afford reclaimed water. This is under an average precipitation scenario. And then looking at social, the initial acceptance rates were calibrated from our survey. So farmers who would fully accept reclaimed water socially began at 10%, and those who would partially accept it began at 30%. And by the time we hit year 30, our acceptance plateaus at 48% for full acceptance. And so after year 30, the social aspect doesn't really influence a farmer's acceptance rate. And so then some agent-based modeling takeaways. Our social network really does impact the reclaimed water acceptance, and it can increase it from 10% to 48%, which is pretty huge. But we still see some economic disparity, and these could be combated with government policies that could acknowledge those gaps and increase adoption. But our models still need to be coupled, like I said. They'll also need to be validated by data and analyzed with sensitivity analysis. And then lastly, here are some potential scenario analyses that we were thinking about. Like I said, one big barrier is cost when we're talking about reclaimed water. So a cost share or subsidy program could be really beneficial for farmers. The USDA NRCS already does this for other natural resource conservation, so it would be pretty simple to implement. Another way would be by increasing the social feasibility scores. So we could increase farmers' education levels around reclaimed water or their exposure to reclaimed water. A study done in 2020 found that farmers were most open to workshops and pamphlets about reclaimed water to improve their education levels, but facility tours are also a really common way to improve their exposure to reclaimed water. And then just some final conclusions. Reclaimed water is a really valuable untapped resource in Maryland agriculture, but we currently have a lot of social and economic perceptions and costs that hinder the widespread acceptance of it. That being said, around 50% of our farmers were open to reclaimed water irrigation if it was proven feasible, so this bodes well for the future. And we can look towards government assistance to maybe improve conditions, but we have to be careful about farmers who are more hesitant about government regulations and programs. So I want to quickly thank my lab members, both from last year and this year, as well as our postdoc, Mohammed Reza, for working with me on the ABM. And I'll take any questions. Yeah.
Yeah, really nice talk. So I'm curious about sort of the survey, and so did you define reclaimed water for the survey? So kind of maybe, what did you say? I'm just curious.
Yes,
yeah,
it definitely will impact, but yeah, you say treated wastewater, I think is standard, yeah.
Okay.
And based on that, yeah, we asked about their comfort about it and things like that.
So you didn't necessarily, or did you field questions before the survey? Like, I'm just curious, you know, this, when I talk about it, even though my class is the yuck factor, right?
Yeah,
So
it's-
I'm kind of
yeah.
curious about that, how you encounter, you know, or did you handle that, or did you encounter that, or sort of, yeah.
I didn't get many comments on it. I
Okay.
mostly, if anything, had comments on like people concerned about their groundwater, which I thought was surprising. Like, you know,
yeah, that is.
that wasn't the biggest concern I had. So yeah, interesting. I don't know.
Yeah.
Yeah. Yeah.
Can you explain more how the social network for the individual agents played into, or was put into the agent-based model?
Like this?
Yeah.
So, yeah, basically in NetLogo, the software that we're using, there are some predetermined structures that you can use. It's called preferential attachment. It's for scale free. And so it basically assigns like the number of neighbors you give it and the like rate at which ideas spread. And so you can manipulate most of these factors, but it's pretty like in there already.
So you took like the survey data, and if an agent was within certain neighbors distance, was it like spatial distance or just like the nearest like?
So the network is different than the feasibility itself. The network just defines who they're the most likely to talk to. So it's not spatially defined. And so the scores are separate from that. You could do cluster analysis, but we didn't make agents that spatially distinct, because we just surveyed by county basically. So I don't have, I don't want to spatialize them, but yeah.
But if they were in a network that had like a majority were in favor, then therefore those agents would have a higher likelihood of also being in favor, is that how?
Yeah, I mean,
it worked out?
they're all connected. It's all one big network. It's not several,
Okay.
Yeah. There are other networks that do that though.
But in NetLogo, though, you're actually, so the rate of, as you mentioned, rate of the connection, you gave a rate factor that affects that at what rate, who is sort of, contacting with the other, communicating. In our previous work also in DC census, we also came up on the other NSF project that we basically, the BMP implementations, if a neighbor had implemented the BMP, this was through different methods, but it actually affected the other neighbors, so it increased the potential for, in a way, but in NetLogo it is more of a by rate factors that are.
Okay, so all agents are in the network. Okay. Depends on who they're next to.
Yeah.
A previous PhD student of Masoud's, he had done cluster analysis. So in that case, you say which agents their opinions are closer to each other, so it clusters into one sort of team. And therefore says, okay, well, this idea that we're going to spread, we want to apply it to this cluster here, which applies all the stakeholders that are within that, or agents that are within that cluster. In this case, there's more of the whole community is one, so they haven't divided to clusters yet.
So the follow-up question is,
Sure.
so you said future sort of things that you could do, one would be like
Yeah.
educational stuff, facility tours and stuff, so I mean, that is like the cool thing about agent-based models, right, is you can run a bunch of simulations and change scenarios. Is that what you plan to do?
Basically, yeah, you can impact certain attributes that we've assigned. So if we just increased education, maybe farmers that had initially rejected it, we send them back through and increase their education levels. What happens? Something like that,
Is that a plan?
Yeah.
Okay.
Yeah. Yeah.
Do you have any ideas about why the estimated acceptance plateaued where it did or when it did?
Yeah, so our social scores are set at like threshold like numbers basically, and those are calibrated based off of our surveys. So I calculated scores from real survey results to find like, who said they would fully accept, calculated the score of all these features that I thought were important, and then set the threshold number at that. And so at a certain point, some farmers aren't going to calculate above that number, and if since the neighboring effect of their network isn't 100%, so it's a chance basically. So if they are interact with someone who is positive, there's a chance that they accept that more, but it's not 100%. Does that make sense? Yeah.
When you were calculating the economic feasibility for each watershed watershed, which number did you use for the cost for water? Because you had a range before, and then
So I tested for all of them. We ran them all. I just showed 10 cents and 20 cents, but by 30 cents, no farms could afford it, so it would have been a blank map. Yeah. Yeah.
For your survey, was part of that used as a validation set for your model?
Yeah.
Right. Just a couple of questions
Yeah.
on the drivers of reclaimed water acceptance.
Yeah.
So reclaimed water acceptance, was that on a scale from like, or was that binary?
It was basically binary, yeah.
Okay, so
Somewhat,
it's
yeah.
just-
It was like yes, partially no. Yeah.
So these are kind of like binary regression.
Yeah, I scaled like all of the factors basically.
And yeah, my next question was farm size.
Yeah.
Predictor.
Yeah, that makes sense. Yeah.
So it seems like, despite the modeling and so forth, proximity's gotta be really important, right? There's only so much water. If you're next to the treatment plant, you might say, sure, it's almost free. And if you're 20 miles down gradient somewhere, is there any sensitivity to that in what you've done, or is that?
We haven't prioritized by distance, like it's not like a set prioritization, but in essence, yes, costs will be lower for those who are closer. But because we have like this like backbone system, we're hoping that distance isn't the biggest barrier here, especially if they're all equally paying some of the main backbone. Let's say like farms who are out here, if they all, like all the farms on this line, if they all split the cost of, let's say, this line, and then farms out here split this line, we're hoping we can limit some of those costs associated with it and piping.
And it's sort of a second question.
Yeah,
You had millions of gallons per year,
yeah,
but you only need this in certain windows. Is there
yeah.
seasonally a real big disconnect in the availability?
So that's another thing. And for our agent-based model, we are considering storage tank as a factor, so as a cost associated. So during off-peak hours or off-peak, months, we can store some water up while we're not really using it. But it's hard to consider that in a model that just runs for the season.
And one last thing, it's probably difficult to relate to this, but working in acceptance to use of biosolids as fertilizer and whether that would influence acceptance. Because
That's
they both have
interesting.
yuck factors.
Yes.
Yeah. Yeah, go for it.
I loved your use of Mr. Yuck. I don't know,
Yeah,
certain
that's what I associated with it,
related
yeah.
to Mr. Yuck, but Southern Maryland has a rich history in electric cooperatives, Southern Maryland Electric Cooperative. Was there any thought of like a water cooperative, and if farmers would have a greater, like farmers generally have more acceptance of cooperatives in terms of, in Southern Maryland and other parts of the country, but was there any thought about that, and would you think that might trip people into more, like if they were part of a larger water cooperative sharing all the costs, and I like what you were looking at the backbones.
We haven't considered that, but that is a really good point, and it would probably avoid a lot of that hesitation towards government regulations and
Right, if
oversight.
they're all a part of the ownership structure
Yeah.
and they're part of the cooperative,
Yeah.
ideally with some, federal or state money to help them do it, but.
Yeah, it might bring in some of the like stakeholder conflict side of things,
Right.
but that is an interesting point, yeah.
Just an additional note on that. I communicated with Andy Staley with Maryland Geological Survey. In southern Maryland, Zakia watershed, that is one of the watersheds, it's really agriculture is not big, as Emma mentioned, that only 15% of the land is agriculture, well, compared to Greensboro watershed, right? So irrigation is not really yet big thing in there. Most of the water actually tapped from the aquifer is for government supplied for municipal use in Southern Maryland, so far.
Right.
So forming, in other words, water cooperatives for the way, reclaimed water, that would be a great idea. It's a futuristic thing. So we are basically at the beginning of testing the potential feasibility of use of things and then go after to see, so what are the barriers that we can actually go after, either cost sharing, forming cooperatives. This is a great idea.
And like contacting, like, I did some project work for Southern Maryland Electric Cooperative and their history, and a lot of the old timers down there were aware of that history and have a positive association with it.
Yeah.
So that might be a way to kind of bridge that gap and to the next generation.
Yeah.
Hi, Emma. It was a great presentation, but when we landed on this page, you might have said it, but I already forgot. This proposed backbone irrigation pipeline system, is this something that y'all created in this proposing, or is this from like other studies or other information that you're adding into your like model?
So that's a good question. So it hasn't been proposed for Maryland yet. These systems do exist in like Colorado and California already, just because it is one of the better ways to distribute reclaimed water if we're not going to use like trucks. But yeah, this is something I just developed like a few weeks ago because we need to optimize the distances. But it just follows the highways. Yeah.
But the use of reclaimed water from waste treatment plant in Eastern Maryland, actually waste treatment plant in Eastern, they are providing free of charge for one of the farms there for the irrigation already. So it's really interesting. But it is close by within the neighborhood, so they don't need like 10 kilometers or 10 miles, whatever, piping. And so that's really a big problem. Another thing that I think we should really consider is that when you use reclaimed water, you save that fresh water in the aquifer, deep aquifer system. So for the future sustainability of water, which MDE colleagues that I work with, they're very concerned about that. And so that helps. That's another added value. So therefore, there comes even if there is distance, there may be a cost sharing possibility that from federal and state governments, just like for other waste management practices, that to be able to implement this practice, so to save the fresh water for future. Because confined aquifers don't recharge in the same location that you withdraw the water. Recharge zones are somewhere else. If you look at the aquifer sort of impeding layers and aquifluids and all that. So my point is, it's a long story, but there are lots of sideline effects that it is not really presented here in this presentation.
Yeah.
So you mentioned how, like with Net Logo, that one of the base models was like this predator-prey type of model. In your agent-based model, like one of the things that was being transferred from agent to agent was like an idea, essentially, right? Is there a mechanism in the model for ideas to get like squashed? Like basically the thing that's being
I mean, yeah, we can have acceptance decrease too. If you run into a really angry neighbor.
Yeah, right.
Yeah, you can do that too. Yeah.
And does that happen?
I currently have it set so that once you've gone up, you can't go back down in acceptance, but we could definitely bring it back in. Yeah, and we currently have it color coded so you can see like green, red, colors of agents based on where they're at socially. Yeah.
Nice.
Yeah.
Really simple question.
Yeah,
I think you said that 76% of your farmers said that profit was their number one motive.
7.6 was the score they rated it.
Oh, okay.
But yes, that was
So were there other top motives for farmers?
Those were the top three. The other motives scored a lot lower. Like these really stood out. Maybe I just messed it up, I'm sorry. But anyway, the top were, and then their second was own experiences, being like, they wanted to trust their own experiences when they're making farming decisions, which intuitively makes sense. And the last would be water conservation. So it was one of the three big concerns when they made farming decisions. Yeah.
Is surface water irrigation ever used, or is that not allowed? You said they have to do groundwater or reclaimed water.
It's definitely allowed.
It is?
There's no, I mean, not in our model, it's not currently included, but it, you know, it could be a potential,
Like that Zakiah swamp that's right in the middle there.
yeah.
Drain that dry. That's maybe not a good idea.
You don't wanna drain wetlands, right?
No.
Pipes running into the Tuckahoe River, Tuckahoe Creek, pulling surface water directly into that region.
Wow.
I just want to add one thing that appropriate to give credit to our postdoc,
Yeah.
Dr. Mohammad Izayaz Samadi, who is continuing on that agent-based modeling. Even will continue beyond, you know, Emma's sort of thesis. My point is, yes, there are lots of other attributes that can be added to that agent, we are aware of that, so we'll see where we get. So he's working on it as well.